So we're going to get into graphing exponential functions. And first, an exponential function is when you have a variable in the exponent. So a similar one or basic one is y equals 2 raised to the x. The base, or what is being raised to that exponent, can be changed. So this is basically a generic function here. F of x equals b raised to the x. And this represents an exponential growth. The reason that it's exponential growth is because it's growing as x approaches positive infinity, y approaches positive infinity. And the reason that it does that is because this b, or the base of the exponential function, is greater than 1. Other parts to this graph, you don't need to necessarily write all of this. This part is important, and the graph is important. So go ahead and make sure you write all of that part more than this paragraph right here. But the domain, because the graph is going to the left and all the way to the right, nothing is stopping it going left and right. The domain is all real numbers, or from negative infinity to positive infinity. The range, though, if you notice, stops right here at the x-axis, and that's because there is this asymptote at this x-axis, and the asymptote basically doesn't allow the graph to go past that asymptote. So the asymptote here, let's skip range and go to the asymptote. The asymptote is at the equation y equals 0. It's a horizontal line, so the equation is y equals, and for the parent function, it's at y equals 0. So that means that the range does not go past this asymptote, or does not go past 0. So the range is where y is greater than 0. But notice that it's not equal to 0. The graph will never touch 0. It will never touch that asymptote. It just gets closer and closer and closer and closer to it. In interval notation, the range is from 0 to infinity. And it has the parentheses because it doesn't actually touch 0. And then the y-intercept is at the point 0, 1. Because no matter what number is here, when I plug in 0 for x, it's something raised to 0, which is always equal to 1. So it means basically that you're always going to have these 3 points. When I plug in negative 1, so let's look at this example here. If I'm plugging in negative 1 for x, because it's a negative, to make it positive, I move it to the denominator, and then it's 1 over just whatever that b term is. So you're always going to have that point negative 1, 1 over b, the point 0, 1, and the point 1b. Because if I plug in 1, that b doesn't change, it's raised to 1, so it's itself. So these are the 3 points to pay attention to: negative 1, 1 over b, the point 0, 1, and the point 1b. So the end behavior for exponential growth is as x approaches negative infinity, f of x is approaching that asymptote, which is at 0, and as x approaches positive infinity, f of x is approaching, it's going up, and that's going to be approaching positive infinity there. So let's look at the other type of exponential function, which is exponential decay. An exponential decay happens when that base, or the b, is between 0 and 1. So when you have a fraction that's less than 1, something like 1/2 raised to the x, this is going to be a exponential decay. So when that b is less than 1 or between 0 and 1, it makes it an exponential decay problem. The domain is still the same, all real numbers from negative infinity to positive. Your range is still from 0 to infinity. Your y is greater than 0. Your asymptote is still at y equals 0. And your intercept is still at 0, 1 because, again, if I plug in 0 for the x, it's still going to make, doesn't matter what that number is, it's still equal to 1. What changes is these points here. And these points are still the same. Except when you have 1 over b, it basically will flip this fraction. So in this case, when you plug in -1 here, that's going to make this y equals 2. So I would have the point -1, 2, which would be up here. And then the right side would be 1b still. So these points are still the same. -1, 1 over b, 0, 1, and 1b. The graph is just going to do this shape where it's decreasing as x increases towards positive infinity. The y value will be decreasing towards that asymptote. And let's add this one more to it, the end behavior. As x approaches -infinity, the y value is going up. So that means f of x is approaching positive infinity. And as x approaches positive infinity, the y value is going down, but it never crosses this asymptote at y equals 0. So it means f of x is approaching wherever that asymptote is, which is 0. So to graph it, I'm going to make a table of values. And I should know these 3 points already. The 0, 1, which is here, and then because this is growth, it's going to be, I should know it's going to be going this direction because the b is greater than 1. So then I'm going to have that point 1b, which is going to be 1, 4, when x is 1, y is 4, and I'm going to have the point -1, 1 over 4, which is going to be about right here. If I plug in -2, well, that's going to be y equals 4 raised to the -2. Well, again, because it's negative, I'm going to move it to the denominator, and that's going to be 1 over 16. And that's why you're going to have this asymptote, is because it doesn't matter how far this gets to be a negative, it's never going to make the y value a negative. It's always just going to be 1 over a larger and larger and larger number here, which makes that number closer and closer and closer to 0. If I plug in 2, I get y equals 4 squared, and that's going to equal 16. And if I plug in 3, y is equal to 4 raised to the third, which is equal to 64. And if you've ever heard the term something is growing exponentially, means it's growing very, very fast. And as you see, I've only gotten where x is 3 and my y values are already at 64. It gets up there very quickly. So in this one, it gets really, really close to 0. And I don't have room to graph the other 2 points. So there is my graph. And I have the domain of all real numbers from -infinity to positive infinity. And my range is from 0 to infinity. My end behavior is going to be, as x approaches -infinity, f of x is approaching 0. And as x approaches positive infinity, f of x is approaching positive infinity. Okay, so to graph other functions, I'm not going to have you do all the points, but I am going to have you do those 3 points that we talked about in the parent functions, and then you're going to shift them based off of the rest of the graph. So draw the parent function and then shift that graph the way it needs to be shifted. So I have here the parent function is y equals 3 raised to the x. That b, the base, is part of the parent function, which is where this is a little bit different than a lot of the other functions we've graphed. So I have the point, again, 0, 1, -1, 1 over 3, and +1, 3. So I have this parent function, and my asymptote is at y equals 0. Well, to graph this function, all the a, h, and k is all the same as it's always been. So this minus 2 is my k, which means it's shifting down 2, which shifts this asymptote down 2. So my asymptote is at y equals -2. And now all these points shift down 2. So when I'm graphing the function y rate equals 3 raised to the x minus 2, basically I'm shifting down 2. All these y values are shifting down 2. So this becomes -1, this becomes 1, this becomes 7, and -5/6 here. And then I graph those points, and that's it. My domain is going to be all real numbers, -infinity to +infinity. My range is now not from 0 to infinity, but from that asymptote which shifted to -2. So from -2 to infinity is my range. My end behavior, as x approaches -infinity, f of x is approaching that asymptote, which is at -2. And as x approaches +infinity, f of x is approaching +infinity. So when it's exponential decay, we're going to do the same thing. We got those 3 points. You still have the 0, 1. You have 1b, which in this case is 1/5. So I have 0, 1, 1, 1/5. -1 is going to be -b, which in this case is going to flip that fraction, is going to be 5. And then if I do -2, that's going to be 25. So I would have this graph here. The domain is from -infinity to +infinity. My range is from 0 to infinity. And my end behavior, as x approaches -infinity, f of x is approaching +infinity. And as x approaches +infinity, f of x is approaching that asymptote, which is at 0. Function. So the parent function for this one is going to be y equals 2 raised to the x, where the parent function for this one is y equals 1/4 raised to the x. And make the table, just do the 3 points, -1, 0, and 1, when x is equal to -1, 0, and 1. And I'll go over it in 5 seconds. Okay, so here's what it should look like. All 3 of these points were shifted right 3 and up 1. So you would have this graph here. All 3 of these points were shifted left 2 and up 1. Now for my domain and range, my domain here is still all real numbers. My range is from the asymptote to infinity. Well, my asymptote is at 1, so from 1 to infinity, and they're both parentheses. My end behavior, +infinity. For the second one, this is exponential decay because the b is less than 1. My domain is all real numbers. My range is from the asymptote to infinity. My end behavior is as x approaches -infinity, f of x is approaching +infinity, and as x approaches +infinity, f of x is approaching the asymptote of 1. Here you go. What is a boxer's favorite drink? Fruit punch! Ah! Fruit punch!